Hi everyone, thanks for joining us. And today we want to talk with you about mobile application developed with cross-platform framework technologies and the security implication of using this kind of frameworks to develop your mobile application. So a very quick overview of the agenda of today. At first, we will provide you with some background information to better understand the scope of the talk, and then what are the most popular cross-platform framework out there, with some statistics, and then we will start getting hands-on, showing you the attack surface of this framework and how the code is stored, and how you can attack this framework both with static analysis and dynamic analysis. And we will show to you some examples of vulnerabilities we found in those frameworks. And after that, we will do our conclusion and try to answer the question that we posed to ourselves. So who we are? I'm Marco Grassi. I'm from Italy, and I work as a mobile security researcher for NowSecure, which is a company based in Chicago, and we do mobile security. And
I'm Sebas Guerrero. I'm from Barcelona, and I work with Marco in the same company doing applications assessments. So, first warning is that part of the slides were made while we were traveling, so we had some jet lags and some other side effects. And we can start with the talk, giving the background introduction. First slide is basically this one, is a graphic. We are not going to enter into details because it doesn't make sense. As many of you may note, basically mobile frameworks are out there because developers were pissed off of developing multiple versions of the same application for different platforms. So they decided to generate a common technology, and they decided to create a cross-mobile platform frameworks in order to create a unique application that were able to run in multiple devices like iPhone, Android, Windows Phone. So basically they have a different core application which might differ from one platform to another one, but basically the main features implemented in the application itself, it's the same for all the platforms, and we will show later today the source code and how to retrieve the application assets and how to find vulnerabilities on it.
So from a technical point of view, how code portability is achieved by those framework, because as we know, on Android you mainly develop in Java. Instead of in iOS, you mainly use Objective-C and Swift, so there is no common denominator here, no shared language, no nothing. So those framework must rely on something else. They could rely on native code, such as C and C++, that works both on Android and iOS. But as you know, coding in C and C++ can be difficult, and it's not like a popular way of development of mobile application nowadays. So instead, these frameworks usually compile their code in a bytecode form, and they run it on an interpreter bundled inside of the application, such as JavaScript weight interpreter, or for example, they use HTML5 technology in order to run portable code between the two different platforms. So far it seems great because we can code once and run in at least 2 or 3 or 4 platforms. But now we must answer some question. How is the quality in the code of these frameworks? And do they introduce additional vulnerabilities in those APIs that they code? And if there is a vulnerability, is this vulnerability shared between all the applications using the same framework? So today we will try to answer this kind of question.
So first thing that we had to do when we started to prepare the research was to detect or determine how many frameworks were available out there for developers. So basically, I don't remember exactly the amount of frameworks, but I will say that there are like 50, 40 frameworks available. So obviously we don't have enough time to find vulnerabilities in all of them. So we have to choose or pick up the most important ones, these 5s. So from top to bottom, we have, for example, PhoneGap, or also known as Cordova Framework, which is one of the most famous or important frameworks out there. Nowadays it contains approximately the 6% of applications in the Play Store. Then we have Unity 3D and Corona SDK, which both of them are used for the same purpose, which is game development. And we also have Adobe Air and Titanium Framework, which, all of us know already Adobe Air. It is very famous because of the vulnerabilities in the source code. And we also have Titanium Framework, which is quite interesting. And basically, the first one and the Adobe Air and Titanium Framework, we are going to show today some vulnerabilities that we found in our plane. And we will show also how to retrieve the source code of the original application. So let's going to start with Cordova PhoneGap. Basically, as we said before, this is a mobile development framework, and because of that, it allows to write mobile applications for multiple platforms. And it is thanks to the use of script languages like HTML5, JavaScript, or CSS. As my colleague Marco said before, they have the main core of the framework is based in Java, and right after that, they built at the top of the core framework the applications functionalities, which has been developed in JavaScript or CSS or whatever. So basically, Cordova is an open source framework, which means that we don't need to reverse engineer the framework. We just basically can clone the repository and start looking for vulnerabilities in the source code, which also, the amount of efforts and time, it's not that big. And basically, it's a bridge between JavaScript and native code. So they basically use Genie functions in order to retrieve the application's functionalities. Something really funny about this framework is that a year ago or something, 2 developers or security researchers from EVM found multiple vulnerabilities in the framework, allowing to execute allowing to perform remote code execution in multiple applications. So today we are going to do a review about those vulnerabilities, and we are going to show what's the main problem with these vulnerabilities and how could it be possible to pawn multiple applications in the market, because Cordova Framework already have fixed these vulnerabilities, but the problem is that developers are not using the latest version of Cordova Framework, which means that they are still vulnerable. So you can imagine like thousands of applications, including banking applications, some sort of social network applications are still vulnerable to these vulnerabilities. And the failures are quite simple, from cross-site application scripting, which is basically similar to cross-site scripting, until the ability to bypass whitelist restrictions or execute remote execution code.
So to keep what Sebas was saying, we will review today also Unity Framework, which, as he said, is a framework for developing cross-platform games. And you can code your games in .NET. So you code them in C#, for example, and the code is compiled in .NET bytecode, and we will see how to retrieve the source code later. Right after that, we will cover Adobe Air, which is a very popular cross-platform runtime, not only on mobile platform, but also on desktop. And it's used from many years ago, and you can develop your project leveraging your skills that you maybe have from the past years, while you were doing Adobe Flash development. So Adobe Air shares a lot of vulnerabilities, maybe because a lot of the code is shared with Adobe Flash Player that is on desktop browser that received a lot of attention from the developers and from the researcher in the past years, and it's still receiving. attentions. But here we are in a different perspective, because we are not in a browser, we are not executing untrusted code or code from a remote location. Instead, we are executing code bundled inside of the application. So basically, these memory corruption vulnerabilities are not so relevant, because you just execute code that you have shipped within your application if you don't do strange stuff.
And right after that, we have Titanium App Accelerator, which is also one of the most famous frameworks out there. Basically, it's more of the same. It's open source, so you can clone the repository, you can search through the source code, and you can try to find vulnerabilities easily. And it's basically developed between native applications made in JavaScript, and they use some kind of interpreter in order to execute the application's main features. And it is based in Eclipse Basic, which is sort of pain in the ass, so you can imagine how things are going with this framework. We also have Corona SDK. As we said at the beginning of the presentation, it is mainly used to develop web games in 2D and also, they are used to focus on game development, and they have the source code right in Lua, and they also have bindings in C++ and OpenGL, just to show some stuff related with graphics. And last but not least, we have Kony Framework, which is more the same. It's a platform to develop cross-platform applications, and the interesting part in this framework is that they use Lua bytecode to store the application's assets. And when you reverse engineer the application, you will see that in the assets folders there is an MP3 file. It is not a song. You cannot try to play the song. But basically, if you reverse engineer that file, you will find all the application's assets contained in there. We still don't know why they tried to use the MP3 extension, but it didn't work.
So, just one more time, what are our concerns using this framework? Our concerns are that if we reuse code, it implies that also the attack surface is very uniform and it's shared between all the apps using the same framework. So if an attacker finds a vulnerability in the framework, it can use it in all the apps that use this framework. And our other big concern is that the code is developed in very high-level languages like JavaScript or bytecode-based language, which makes the reverse engineering process very easy or non-existent. So let's start with our first practical part of the talk. We will analyze the format on which this framework stores the code, and how to retrieve them, and how to reverse engineer the code. So, as we said before, if you have a great portability, you have to sacrifice something else. In order to achieve portability like the Java platform, you have to embed a lot of metadata, and so this implies an easier reverse engineering process because of the amount of information inside. So, let's start with the easiest framework to extract the source code. It's PhoneGap, which has the code developed in JavaScript and the UI in HTML5 and CSS3. And the code is not obfuscated or compiled. It's just embedded inside of the application in plain text. So, as you may imagine, retrieving the code is pretty trivial. On iOS, you can just grab the application and look into the www subfolder of the application bundle. And on Android, it's usually the same. And the code is bundled in the asset subfolder inside of the APK. Here we see some example. For example, here we have the Amazon application, which for some functionality, it uses the Cordova framework. And as we can see inside of the application bundle, we have the JavaScript code. At the bottom, we have another custom-made iOS application, and the code is as well in the main application bundle. And on Android, it's the same thing. Here we have another bank application, which have the source code inside of the www folder, inside of the asset one. And as you can see, we can more or less retrieve what the developer embedded inside of the application. So our intellectual property is lost. I mean, it's not protected.
Problem with the previous screenshot that my colleague showed is that as soon as you have access to the mobile application's functionalities, you can modify the source code. So sometimes it's pretty easy to exploit vulnerabilities like SQL injection or cross-site scripting vulnerabilities, because most of the time cross-platform developers don't apply security mechanisms in order to sanitize the input introduced by the user. So shit happens sometimes, I guess. So, for example, with Titanium Framework, in this case, the real code is written in JavaScript. So when you reverse engineer the application and you try to analyze the global security deployed within the app, you will notice that the real source code is not available. So after doing some sort of black magic, you will find that the real source code of the application is loaded by the asset crypt implementation class, which basically loads an asset data at runtime. This means that every time that the application is populated into the device, it will decrypt a chunk of data and it will load it at runtime. So basically, we will show it later, a couple of screenshots on how to retrieve the source code, but they have shared assets, a shared buffer, array where they put all the encrypted applications, user interface, and applications functionalities. And then they also have a hash map which contains all the names of the different files that compose the application's real source code, as well as the offsets where you can extract and obtain the real source code. So, as I said before, we have these two screenshots. First one is basically the hash map, where you have the file names, all the files that compose the real source code of the application, and then we have the range in bytes that belongs to the shared buffer map. So basically you have the initial point where the file starts, and then you have the offset where the file ends and starts the next one. And right below this picture you have the shared buffer that we said before. It is encrypted, and basically all the application's logic is contained in there. So problem with this is that at first instance, when you reverse engineer the application, you will never have access to the real source code. So you have to identify it and you have to decrypt it and extract all the information. And how to do this? Well, at the end of the talk we will release a Python script, but basically what you have to do is to parse the original source code and use those couple regular expressions. First one is to extract the ranges of the files and the file names, and second regular expression is basically to retrieve each portion dedicated to each file name and its original source code. So I mean, I'm not going to enter into details. We will make public the slides and the source code, and if you are interested, you can always go to our GitHub and read through the source code. Once we have retrieved the original source code that composed the application, what happens? Well, it happens that at least Titanium Framework have encrypted the assets, so no direct access is possible. You have to decrypt it, but it doesn't matter, because if you reverse engineer the shared library, libtverify, you will find there the source code used to decrypt it. So it's so easy that you can basically copy it and paste into your script. You can execute it and you will decrypt all the data. I mean, it doesn't make sense, honestly, using this encryption, because it took like 5 minutes or 10 minutes to decrypt all the source code. So yeah, in our theory, so show me some real stuff. Well, in this case, as you can see, you execute the script, you pass the class's doctext file, and it will automatically retrieve all the JavaScript files, and you will have access to it. So you will be able to modify or analyze the real application source code.
So Sebas showed the Titanium accelerator framework, and now I want to show to you the Kony framework, how the code is stored and how to retrieve it. As Sebas mentioned before, if the developer uses Lua code to code their application, the code will be stored inside of an MP3 file, which is funny because it's not an MP3 file, it's a Lua file, obviously, that will be loaded and run by the interpreter. And we don't know why they even put the MP3 extension, because it's kind of a funny thing. And you can retrieve this Lua bytecode, which is not obfuscated or encrypted, and you can just decompile it with open source decompilers for Lua. As you can see at the bottom of the screen, it's possible to retrieve all the functionality of the application. For example, here there is a tampering detection mechanism. So as you can imagine, it's very interesting to look into this kind of functionality implemented in the application. Last but not least, there is a Unity framework which is coded in .NET, like we said before. And if it's not obfuscated, it's very easy to decompile, because the .NET platform is really good in terms of decompile. You can use, for example, ELSpy, which is a very good .NET decompiler, and you can just start reversing the code from there. And Adobe Air, which is very famous, like we said, they are storing the code in SWF file inside of the asset folder on Android. And it's trivial as well to reverse, like the Unity one, because a lot of the compilers are available for Flash. So you can just start reversing from here as well. So so far we have used only like static analysis, but what can we do with dynamic analysis? So we will show to you some application of runtime manipulation on attacking this framework. So what about runtime attacks? Can we use the shared code base like we did with static analysis? Obviously yes, because if we share the code, we can develop an attack at runtime, and it will work between all the applications with the same framework without any change. So to show an example to you, we have developed an attack to buy stuff for free on Adobe Air application with in-app purchase. So here there is a high-level overview of what we did. So at first we reverse engineered the Adobe Air code related to in-app purchase on Android. And we found how they implemented the in-app purchase mechanism on Android. Right after that, we checked that this code was shared between multiple applications, and it was not something introduced by the developer. So in this way, we can check if we can use our attack on multiple applications, and we can make purchase in-app purchase for free. Our attack will make the purchase appear legitimate when in fact we didn't pay for it. So here we have a simplified version of the code for in-app purchase in Adobe Air. So basically they copy and pasted the examples from Google about in-app purchase. So at the end of the day, there is some function that returns a Boolean if the purchase is verified or not. So what we did is at runtime we patch those methods with a variety of framework. For example, we can leverage Exposit framework or Cydia Substrate or your Frida or your favorite framework to do runtime patching. And if the application doesn't check the signature of the purchase on the server side, doing this modification, like returning true in the method that I showed to you before, will just make the application believe that the purchase is legitimate, and it will provide you with the item, like for example a game item for free, when in fact you haven't paid for it in the Google Play. So if you want some more information on how to develop runtime attacks, unfortunately today we don't have the time to go into details, but you can check my presentation at Zero Night, which is only on runtime attacks.
So yeah, that one was an attack against Adobe. As you can see, nothing strange coming from them. And now we are going to explain some vulnerabilities in the frameworks found after doing some static analysis. This is a tale about shiny the vulnerabilities in Cordova framework. This is the one that we explained at the beginning of the presentation, the one about achieving remote code execution. Everything started with a cross-site application scripting in Android intent URLs. Then it goes through a whitelist bypass for non-HTTP methods. And right after that, it is possible basically to perform applications leakage of information against other applications through URL loading. So basically, as you may know, Cordova-based applications renderize the website requested by the user through a WebView component. And the problem with this is that the Cordova WebView activity loads the URL through this function, load URL. So I'm going to show you later the source code of this functionality, but basically, if the URL provided is about semicolon blank or JavaScript, it will be loaded via load URL now method. Otherwise, the register v0 will be overridden by the URL provided by the user. And how this is overridden? Well, it is overridden through the getProperty method, which basically calls the getIntent, getExtract method. This means that basically the parameter received by this functionality can be provided from outside. So, I mean, 2 plus 2 is 4, so basically if you provide to this parameter a malicious URL, you will exploit the user and you will trick the user. So basically, first the screen on the left, at the top left, is basically the load URL implementation. As you can see, it basically performs a check. It checks if the URL is equals to about semicolon blank or JavaScript, in which case it will trigger the load URL function. Otherwise, it will call the getProperty functionality, which we have it in the second screen, and basically it retrieves the parameter through the getIntentExtract functionality, and it will load it automatically into the web view. So at the bottom of the screen, we have the exploit to trigger this vulnerability. Basically, we call the intent action view and the intent category default, and we pass as a parameter the URL, which in this case is basically a local file stored into the SD card, which is a malicious test.html file, which contains itself a malicious JavaScript, which basically will steal all the information from the application's database and will send it to a remote server. So, yeah. Right after that, we only have to pass the package name of the application and the activity of the application. I mean, this is a really simple attack. Problem with this is that these frameworks are used by banking applications, and if they are storing the user's information, well, you can guess it. You will be able to retrieve all the information related to the customers. But there is also another vulnerability with another parameter, which is error URL, which basically is the same as the previous ones explained. The only difference is that this one only works when there is a network request fail, which means that, for example, you are surfing on internet and suddenly you didn't get connectivity. So this parameter will be triggered, and by so there is a chance for an attacker to exploit the user through this component. Basically, it's the same. It doesn't deserve to be mentioned more in details. And second vulnerability basically is that the framework overrides the should intercept request method to ensure that the web view only allows certain protected or checked methods in order to show the request, the website requested by the user. So this is sort of kind of a whitelist security check. problem with this is that they are only checking HTTP or HTTPS protocol, but they are not checking WebSockets or WebSockets under SSL or file XChem. So if the attack doesn't work through HTTP or HTTPS, it doesn't matter because you can exploit the vulnerability through file or through WebSockets. And last but not least, we have another vulnerability, which basically is a combination of the first and the second one. It allows to use a customized URL through the ABAD implementation over the should override URL adding method. So nothing special, honestly. Basically, I mean, the global or security deploying the framework sucks, and because of that, it is quite easy to exploit a vulnerability and get all the information from the user.
Okay, now we would like to show to you some new vulnerabilities that we found in the framework that we didn't disclose before. And the first one is a quirk in the implementation of the APIs inside of Adobe Air on Android. So let's take a look at the documentation of Adobe Air, in particular in the encrypted local storage API. And the documentation says that this class should be used to store credential and other sensitive information, and they will be encrypted and they will remain private to the application. And we will see how this is not true and how we can exploit that. So this is the first vulnerability or quirk on Adobe Air, which is that the real implementation of the class on Android is not, it's called encrypted local storage, but actually is not encrypted. So Adobe basically rely on the fact that on Android you have the Android sandbox where every application runs under a different UID, so each other application cannot access their other private data. But as we will see in a few slides, this assumption is not always valid, because an attacker can retrieve those information without being root. So if you say a developer that your data will be encrypted, he will probably save in their password or username or a credit card or whatever. And if you don't encrypt them, you lie to your developer and you create vulnerabilities.
It's Adobe. What do you expect?
What's the implementation of the encrypted storage class? So as we say, it should be encrypted, but actually compiling the code reveals that it's not encrypted. It's just encoding the data in base64 and saving them as a shared preference in the Android private folder of the application. So this is only one quirk that we found very quickly. The problem is that if there is this kind of very trivial and stupid quirk, you can imagine how many others there are out of there. So, and it's kind of annoying to check all of them because you have to decompile the framework. So, as we said, this data will be stored as base64 in the private application folder. But how an attacker can retrieve that? Well, there is a new functionality introduced in Android 4.0, which is ADB backups, which imply that if you have a physical access to the phone and you can activate the USB debugging, you can backup the private application folder that have the allow backup flag in their manifest set to true. The problem is that if you omit this flag, like Adobe Air is doing, the default value kicks in, and the allow backup flag will become true. And in this way, an attacker can backup the private folder of the Adobe Air application and retrieve these data that are not encrypted. So if a developer saves a password as an encrypted local storage item, an attacker can retrieve them, and they are not encrypted, so they are not protected. And so we are leaking private information. Enough of Adobe Air. Let's talk about Titanium Accelerator. And the first thing we want to cover is that often this kind of cross-platform development tool come with their own IDE. Titanium Accelerator comes with his own customized Eclipse IDE-based IDE, which is called the Titanium Studio. And if you install it on Windows, it will actually install you an outdated Java version. So as you will inherit vulnerabilities contained in this outdated version. Remaining in the Titanium framework, there is actually a vulnerability in their own implementation of the HTTPS client on Android. As we can see, maybe you are doing an application assessment, and you find this. You are able to man in the middle HTTPS traffic. So you start digging, and you ask yourself, who made the error? It's the developer or it's the framework? Because if the error is in the framework, it's much more severe vulnerability because it's shared between all the applications. So why these applications are vulnerable to man in the middle on Android? Well, there is a broken implementation in the default settings of Titanium. So basically, if the developer doesn't specify a certificate pinning for his certificate, the framework will simply accept any SSL certificate by implementing his own custom class, which are called non-validating SSL socket factory and non-validating trust manager. So as you can imagine, they are not very validating anything. So the result is that if you rely on default settings in the framework, like 99% of applications are doing, you are vulnerable to man in the middle. And so it's a very severe vulnerability. Here we show to you the compilation of their implementation of the source code. And as you can see, if you don't specify your own PIN for the certificate, those default class kicks in, and they will accept every certificate. Here there is their trust manager, which basically is invoked every time you must validate a SSL certificate. And as you can see, when you have to check the server if the certificate is okay or not, they are simply declaring an empty function, so they are not validating anything. So how can you mitigate this issue? You can mitigate this issue by using the API exposed by Titanium to declare a certificate PIN. So it's not very user-friendly to do it, but at least until they fix it, you can mitigate your issue by pinning your certificate.
And just to finish the slides, we have the conclusions after doing this very quick research. As you can see, security is not something taken seriously by applications cross-platforms frameworks, and the mechanisms used by them to protect the user's assets are not good enough. I mean, it just took 2 hours or 3 hours to retrieve basically all the application source code. So if we were able to do this without basically a high-level skill sets, anyone can do whatever they want with this. And as we said, a few hours were necessary to do this. So it just forced us to think if the applications that we are running in our device, the applications that we are trusting and providing our credentials or credit card information, banking information, social network information, etc., it makes us think if they are really secure or not. So next step that we decided for our little research is basically to generate some sort of suite available for the attendants or for anyone interested, where you can basically pass an APK or an IPA file, and it will basically detect which application framework is being used, and it will allow the researcher to retrieve the original source code. So basically what we want to do here is to merge all the code extraction utilities that we've made in one simple utility, and keep finding more vulnerabilities in the framework, because we only did this in a few hours. So we think that if we put more efforts on this, we will be able to find more serious vulnerabilities. And if the attendants have some kind of suggestions or questions that we can provide to us, it will be appreciated. So last but not least, as we said at the beginning of the presentation, we work for NowSecure, which is a company based in Chicago, and we basically do remote work, and we are hiring. So if anyone is interested, we can have a little chat.
Yeah, or we can grab a drink and talk, or you can ping us on Twitter, whatever works. And also, if I can add something to the next steps, we will maybe deploy some kind of more advanced runtime tracing for this kind of framework. For example, we may want to instrument their own runtime to trace the execution inside of the interpreted code. So that's it. Thanks for joining us. And if you have any question, feel free to ask us now or later, as you prefer. Thanks.
Yeah, so I was just wondering with regards to Adobe Air, because in the initial chart it showed that Adobe Air was the third most popular framework, but as like a mobile developer, I haven't seen that as often. So I'm just curious, simply because I cannot see right now the SWF being as fast as other frameworks that compile to native code. What is your perspective on why Adobe Air would be as popular as the other frameworks? Yeah.
I think you are right in terms of performance. It's probably behind the other ones, but probably its popularity is due to the fact that there is a lot of developers that have skills on ActionScript or Flash, and so when you have this kind of offer in the working market, you probably end up having a lot of applications simply for the fact that because there are a lot of developers with this kind of skills, and also maybe because it's used also for gaming, so maybe a lot of developers just took their old Flash game and ported in the mobile application to have another additional revenue from it.
And as for a follow-up, just regarding obfuscation, so based off the deobfuscation method you guys used for each of these frameworks, what's your opinion about their use of obfuscation in general? And do you feel like there are obfuscation methods at the app level in terms of actually obfuscating the entire APK or app bundle that are more effective than just individually obfuscating the assets?
Yeah, so suggestion would be to don't use this framework if you have to protect any intellectual property, because simply as we show it to you, your intellectual property is not protected enough with this kind of high-level coding. So if you have intellectual property, maybe it's better to remain in the native code side of things. In this way, you can, even if you remain at the Java level on Android, let's say, you can use obfuscator starting from ProGuard, which is free, going to DexGuard, which is proprietary, but it has a nice price. Or maybe you can use LLVM obfuscator to obfuscate your native code and do even better, or stuff like this. So so far in our research, we haven't seen any kind of obfuscation applied in this kind of cross-platform mobile tool. So I think the answer to your question is that they are not applying any kind of obfuscation. It's up to you as a developer to apply it. So for example, maybe if you are running a Cordova application, which is JavaScript, the logic, you can maybe leverage a JavaScript obfuscator, which is pretty popular in the web development world.
Thank you.
Well, welcome. Questions? Okay. Okay. Thank you.
Okay, thank you.